All right, according to the time schedule, we are kicking off afternoon session. And I'm seeing people actually are coming back to the seats. So in that sense, let me directly jump into the highlights of the programs for today. So first of all, in the afternoon, we will have one of the interesting keynotes who is going to actually set the tone and also the scope for today's afternoon discussions, which is about the edge, the AI, and also the sustainability concerns. And then in that sense, you are expecting actually a diverse topics going to be covered, but then have a central line of connections is about sustainability. And then that's the whole point of this afternoon. And also, as many people remember in the morning, the edge of the network of the power grid has been mentioned several times. And then in the afternoon, we have several talks directly going to the edge and then to show you what is actually the problems and also solutions, innovations people have already been made. So without any due delay, let me just pass the mic to Suzan, who is actually now the director of 40U ICT, and it's my honor to actually invite her for keynotes today here. So.
Thank you very much, Aaron. My pleasure to be here. Is the distance ideal? So you can hear me from the back? Okay, good. All right, so, well, good afternoon, everyone. I will be talking about ICT, sustainability. So I believe as people working on energy transition or power systems, you are familiar with the challenge of sustainability, right? This is one of the biggest challenges of our times, I believe. And ICT is part of the solution, but also part of the problem. Solution part is, I believe, clear to many of you, but maybe the problem part is not. So that's why in my talk, I'll try to give you some high-level insights about why we need to work more about the sustainability of the ICT, okay? Thanks. Afterwards, I'll try to give you also some approach from the recent literature and also to be more concrete about our own research on mobile networks. So what are the directions to make systems more sustainable? And then in the final part of my talk, I'll try to connect the story to power systems, okay? Based on my understanding from the literature. So with that note, let's get started with the bits. In the past decade, the number of connections, the number of people connected to the internet has doubled, which is really great news because we are closing the digital divide. This is really nice. The number of bits we consume and generate also increased, but increased at a very high speed. For instance, the global internet traffic increased 25 times, and when you look into your mobile phones, it is 300 times or so. So we enjoy our cute cat videos, wonderful, we consume and generate a lot of data. However, this has a cost. Cost for, of course, manufacturing the devices, all the infrastructure, but also collecting the data, generating the data, we call it sensing, and communicating, transmitting the data to where it is consumed or where it is produced, where it is processed, is taking resources, consuming resources, which you could translate into watts, for instance. Of course, data needs to be stored. Data needs to be secured, as you have discussed in the morning. All coming with its cost. And when you look into the numbers, then you would see wide differences, actually. But the most credible resources say the ICT's electricity consumption is somewhere between 4 to 6% of the global electricity consumption in 2020. And when we look into the emissions, so GHG emissions, it's on par with aviation industry, somewhere between 2 to 4%. When we look a little bit closer to this, ICT, so communication, networks, and devices, we see for all these components, actually, there is a growing electricity demand. I think no surprise to you, right? So when we look into those in the past years, you would see devices have a huge demand because we have billions of devices. Next comes the data centers and the networks. When you look into the networks, then mobile networks demand more than the fixed networks. So all these increases, okay? However, when we compare it with the increase in the bits, you would say, actually this increase is modest. So you don't see 100 times increase in the electricity consumption or the demand. This is good news, maybe, I'm not sure, but there is a lot of technological advances in hardware and software in the past decade, thanks to the efforts of many scientists, engineers, regulators all together, right? Good news. And we are done? Actually not, because of various reasons, but I'm going to list 3 of them. So first thing, sustainability is beyond, of course, electricity consumption. So we need to look into the whole life cycle of the devices and services. So for example, the raw material extraction is an important part of the whole life cycle. Manufacturing, distributing, use, and later electronic waste. It's a huge problem. So we can consider both embodied and operational cost of all these digital systems. That was the first reason. The second one is actually toward net zero by 2050, we have to do much better than modest increase in electricity demand. Actually, the intermediate goal, 2030, all the sectors need to decrease their emissions by approximately 50% or so, Fit for 55, for example, by 2030. And for that reason, the whole digital systems and whole sectors actually need to decrease their emissions drastically. And the third reason, AI. So all the figures I mentioned actually come from the years where AI was not so ubiquitous in our daily life, right? So now it has changed, in my opinion, the story quite dramatically. Every day you see some news about AI and how power hungry it is, so how it would affect the digital energy systems and consumption. So I hope we all feel like there is a problem here, and let's talk a little bit about also potential solutions. I like Green Software Foundation. They really have a emerging, a community thinking more about the greenness of the software, and they introduced these 3 principles, and I believe they are also applicable to any digital system. Energy efficiency, hardware efficiency, and carbon awareness. So the first principle is consuming the least electricity possible, and the second one is consuming the least hardware and hence the embodied carbon possible, and the third one is carbon efficiency or carbon awareness, so being aware of the carbon intensity of the electricity sources and doing more when the sources are cleaner and less when it is not. So I think the first one is probably easier to get from the description, and let's have a look too, especially the last one. But before that, when we look into the life cycle, we see different dominant factors. So for instance, for hand devices or battery-operated devices, the embodied part of the emissions seem to be more dominant. Some numbers, but for instance, for iPhone 13, it was like somewhere between 70 to 80% of the emissions coming from actually the manufacturing process. Also because hand mobile devices are really being used only a couple of years, which is a problem that turns out to be an electronic waste. When we look into the network and infrastructure devices, then not a single number, it's difficult to find, but most of the time, operational side of the emissions seem to be more dominant, generally speaking. So the point is, of course, for different things, handheld devices versus network equipment, we can approach the problem from different angles, but I would like to say both are important, both needs to be decreased. Now, the third sustainability principle, the carbon awareness, is something to do with the carbon intensity of the electricity resources. So mainly it measures how much carbon equivalent emissions are created because of 1 kilowatt hour electricity consumed. It turns out, I think this is not surprising, depending on the time of the day and the season, you would see different carbon intensities, and the lower is better. So this plot shows for the Netherlands 24 hours on the x-axis and the 4 seasons. And actually, there's a huge difference for the same month in the 24-hour period. It's not only during the day you would see different carbon intensities, but also at different locations. For instance, this is the world map, and the colors greener, the better in terms of carbon intensity of the grid. Nordic countries are doing well. Belgium is doing better than the Netherlands. So the computation can be actually maybe shifted to different times, different locations, if security and other regulations or privacy regulations allow. My point is, there is some flexibility, let's say, due to differences in carbon intensity of the grid. Now let's talk a little bit about different solutions. Since edge computing was mentioned, I believe it is also good to think about how it can actually help in the sustainability challenge. In different environments, you would have sensors, devices collecting data. It could be a smart home environment where you have many devices for the comfort or energy saving or for health purposes. It could be a smart factory. It could be a smart agriculture setting. All having their own different requirements. Smart homes, very important to have privacy. Maybe agriculture, not that much. Maybe there is still privacy problems there as well. The data being transmitted to some backend which does the processing to gather insights and actually to decide on the most efficient operation mode. Most of the time it is further away from the end users, and the data needs to travel, meaning it goes through networks, adding latency, but also consuming resources which could be translated into carbon emissions. The idea now is bringing compute closer to the users or generators of the data, so you don't need to transmit that much. And actually, this can also offer, for instance, latency benefits or privacy benefits, because rather than computing somewhere in the cloud, you could do the computation at home. By the way, edge depends on who you are asking to. So is it the telco edge? Is it the home edge? Is it the extreme edge on your smartphone, etc.? But it is close to the user, the consumer, and the producer of the data. It could actually offer also maybe power saving or energy saving, because you don't need to transmit the data all the way to somewhere else in the cloud. However, I'm asking whether we are losing from economies of scale, because in the cloud you have lots of multi-tenancy benefits. Maybe in edge, if we don't have these multi-tenancy benefits, then we don't gain that much. That's the question. We also have maybe new compute units deployed. So does it mean we introduce additional embodied carbon? However, of course, not only the edge or the cloud would solve the problem. That's why we like to refer to it as edge to cloud continuum. Depending on the user application requirements, the resources, the idea is to utilize this continuum for achieving the trade-off between efficiency, latency, privacy, and hopefully also carbon footprint or environment footprint in general. Actually, it is also advocated in Europe's Digital Decade Agenda. So mainly by 2030, the idea is to have 10,000 climate neutral and highly secure edge nodes deployed in Europe. So to serve the citizens and the compute needs, which I believe becomes more and more relevant with all these AI agents and so on. We also see in the literature carbon-aware computing. So for instance, data centers actually are the distributed infrastructures. They have different compute units in different parts of the world. Maybe these differences could be used especially for compute that doesn't require real-time response, like AI training, or some backup operations or big data processing. We also see in this figure the networks. The internet works on determines the routes from autonomous system 1 to 2 without actually paying much attention to the environment cost. And now we see some studies talking about, well, maybe we should introduce the carbon cost of the routes from system 1 to system 2. And because of the difference in different autonomous systems and their energy sources. Actually, another thing, if we zoom into the devices, we see that this is also similar for instance, modems at home, routers, etc. There is a lot of energy consumed even though the device doesn't do the actual work. So that is the idle power part. So this system is on, consuming a non-negligible amount of energy. And then, for instance, different ports for the routers, they have some additional cost in terms of power, and the dynamic cost is about how much traffic is routed. So the idea is maybe some of this equipment could be switched off, or the ports could be switched off to save from power. Also, another level now, websites. So depending on the website design, you would see different carbon costs. Actually, this is from the tweedekamer.nl. So the report EcoGrader gives us whether its energy label is A or B or C, or it goes down to actually E. So because of the image size, because of the scripts, but good news is that they are being hosted on some green hosting service. Nevertheless, things for improvement for the tweedekamer. In short, from hardware to software, from networks to data centers, from carbon awareness to hardware efficiency, there's a lot to be done. Also, it is maybe about digital consumption behavior, regulations, and policy. They all need to be improved to make systems more ICT, more sustainable. This was a little bit high-level overview, but I would like to be a bit more concrete and tell you a bit about our own research, which is on mobile networks. So mainly, our question was, well, how can we make mobile networks more sustainable? So one thing, I love mobile networks. They are wonderful, especially in the Netherlands, so densely deployed for coverage capacity, but also for meeting the requirements, regulations. For instance, in the Netherlands, RDI requires the minimum data rate of 8 megabit per second, 98% coverage, so they are densely deployed. Wonderful. And actually, when you look into the deployment map, you would see they are everywhere. And actually, I checked it also for our location now. I think we are surrounded by, I don't know where they are, but there are many. So around 20 to 30 towers are there, right? So your mobile phone might be getting high quality signal from many towers, which is wonderful for resiliency. If one fails, the other is there to serve you. However, they are most of the time over-provisioned, so their utilization is low. Maybe some room for us to explore whether we could, well, save from power there. When we look into the mobile network, we see that the base stations, the antennas, actually, they are consuming the biggest part of the electricity in the network. And when we look a little bit closer, operational versus embodied, we see that most of the emissions come from the operational phase. That's why we, most of the time, focus on radio access networks, so base stations, and at the operational stage. Now, power consumption of these devices. There is some constant side power for cooling, etc. Also, there is idle power to keep the equipment on, which is also non-negligible. And there is some load-dependent dynamic transmission power, which depends on the transmission power level. Okay? So, our research mainly asked this question. I guess you are familiar with the international roaming. So when you go to another country outside of your own subscriber's country, then you can connect to another operator and get service. And a similar idea, let's do it in the nation. So my mobile phone is from one operator, but maybe another cell tower is better for me because it's closer, or because its signal quality is better, or because it would lead to better or power savings and so on. So we asked this question, what happens if operators just, serve each other's user if it turns out to be better in terms of power savings or capacity and coverage? So the idea is, here in this example, we have two operators, MNO 1 and 2, and this user is actually operator 1's user, but there is no signal let's say, high signal quality here. So this user is under coverage hole. But actually there is another base station from another operator. So this user could connect to this other operator's base station, and we solve the coverage problem. This could also be useful, not to solve the coverage problem, but actually to facilitate higher signal quality. Because generally speaking, if you bring transmitter and receiver closer, then transmission signal quality will be higher. Or for the same signal quality, you would have lower transmission power, which is good for, well, decreasing the power consumption of the network. Or if one base station doesn't have many users, and we could actually steer the user of that base station to another one and switch that off, and be safe from idle power. Okay, seems like there is some promise here. But our question was, to what extent can we save? Is it like 5% savings or so? And we wanted to do this analysis. One is very hypothetical. All the infrastructure operates as it's a single infrastructure. No matter which operator you are subscribed to, you just can connect to any of those. And the second one is more realistic. If my operator cannot provide me sufficient signal quality or sufficient data rate, then I connect to another operator's base station if that can provide me what I need, right? So fallback. In the background, if you are familiar with the Shannon's theoretical capacity, we mainly calculate the capacity of the channels, considering the available bandwidth, the signal quality that depends on the transmission power, the distance between the user and the transmitter and receiver, and the propagation conditions of the wireless environment. Then we calculate what is the needed minimum bandwidth you would require to meet the application requirements. So it's video, I need 5 megabits per second, for instance. In the background, we do lots of optimizations, how users should connect to the base stations, how base stations should adapt their power. So we find the point of operation where the energy is minimized, but all the requirements of the applications are met. Of course, lots of assumptions, lots of modeling decisions in the background. So with that caveat, I would like to say, hopefully our models are useful to give insights about the potential, right? Now, we use the cell tower data from RDI and antenna cards. We know the locations of the antennas, their frequencies, operation angles, height, and so on. We have the population data from CBS for each zip code to understand the traffic intensity or to mimic the traffic intensity in each zip code. For the wireless link propagation environment, then we have the channel urbanity levels mapped into the channel models from 3GPP, and then we calculate the power consumption, the coverage capacity for all those. I'm going to show you only the power consumption. The other factors are almost the same or even better for the hypothetical best case scenario. So this green bar shows the current way of operation. So operators do not share their infrastructure. And this blue one shows the hypothetical setting where all the infrastructure is operated as a single one. So we see significant savings in total power consumption. Okay? And when we look into the fallback, we see that the power consumption in the whole country in the cellular infrastructure increases because now we close the coverage gap. So we gain in connectivity rather than the power. When we look into individual MNOs, so how do they perform? Actually, when all operators serve or collaborate, then they can decrease their power consumption because they serve users that are closer to themselves and transmission power is decreased and they benefit. However, if it is more like collaborations are based on fallback scenario, then some operators gain from power, like the third one. Others do not, because the operators with better infrastructure now serves the other users, so there must be some monetary settlement for sure. In short, you could also unlock many more benefits by optimizing, for instance, switching off the base station sectors and maybe if under low load, some cells as well. So actually, this is not a crazy idea. So in some of the policy documents, you would see infrastructure sharing as a promising direction for future greener mobile networks. Now, I would like to connect the whole story to maybe to the power grid. So, of course, I talked about the ICT communication data centers, networks, and the devices as if they are in a vacuum. Of course, they are not. So they have to be powered. They are creating demand for the grid, for the power network. And when we look into the networks and data centers part, actually we see two differences. We see a difference. First, data centers are clustered. So for instance, in Europe, Frankfurt, London, Amsterdam, they are the hubs. They host a huge data center infrastructure. That means those are the points where there is a stress for the grid, or there is a problem for the data centers because the grid actually doesn't have the capacity. When you look into the mobile networks, or networks in general, they are more uniformly distributed because, of course, some regions are, more densely deployed than the others, but still the infrastructure needs to be there. Actually, the report from Joint Research Council also mentions the electricity consumption for broadband communication networks and also the data centers. And for data centers, it's in EU 27, countries. And then you see a huge variation in data center electricity consumption, 18% being in, any guesses? Not Amsterdam for sure, but in Dublin, so in Ireland. For broadband networks, it's more like 0.5 to 1.5. Countries with bigger population, they have more, but more or less it's the same for countries. So what does this mean? As I said, maybe also I saw the news, Microsoft CEO says they have the GPUs for AI compute, but they don't have the power to put the compute into operation. So this means, well, either data centers need to go somewhere where there is the grid available, a capacity available, or the grid capacity should be thought beforehand for accommodating the AI data centers and so on. Of course, we should not forget about the sustainability issue, okay? But this is one thing maybe related to power systems. Actually, there's a report talking about these data centers and importance of planning the grid based on the need for AI and AI factories or all these infrastructure. When it comes to the mobile networks, also there's a lot of discussion about mobile networks and how they can actually become part of the especially fast power reserve market because mobile networks, they have to be resilient. They have to offer continuous service even the power system is disrupted. So, for instance, they have batteries at some locations, and those batteries actually could become useful for the grid in, they say, fast power reserve market. And also this could be considered as a flexibility to leverage for the stability of the grid or for maybe renewable energy storage. So to finalize, I would like to say there are many efficiency improvements for sure in the past decade. Software, hardware, technologies, all the ecosystem around that. But actually, the sustainability challenge requires us to think more and actually decrease the emissions rather than keeping it at a modest increase level. And the sustainability principles need to be implemented from hardware to software, from data centers to networks to devices. And I believe more interaction between the power systems and the mobile networks or whatever ICT component you are considering needs to be considered. Otherwise, these systems are optimized separately and then they, either hurt or the other one or be constrained because of the constraints of the other system. So I think that's it from my side. Thank you very much, and we'll be happy to take comments if any.
burning questions, feel free to raise your hand. First come, first serve. And then, yes, go ahead.
Should I give?
Okay, you can have that. So thanks for the great presentation. One quick question, maybe if you go to the previous slide. I'm really curious to know if this has been tried out on actually using mobile, network towers which have batteries to actually deploy them on the grid as distributed energy resources, or to actually support the grid. And what kind of impact have you guys modeled in terms of the resiliency of the mobile network itself? Because if you start using that asset in the grid, then is there an impact on the network services itself?
This is not from my own research, but this is from a report which was published only July 2025. So I believe developments are quite new. So in practice, I don't know whether they are indeed in the market, but I believe this is the kind of policy or strategy document suggesting this could be done, but I don't think it is implemented. And when it comes to resiliency, important question, let's say. I don't know how it might affect indeed. Yeah. Thanks.
I think respecting the time, we were collecting questions over the QR code and then having the panel in the end for responding to all the questions overall. So let's thank Suzan for the inspiring keynote. Okay, thank you. In terms of today, I think it is actually community building as we mentioned. So in the morning, I heard already that many computer scientists, many kind of, I would say, AI experts, they are actually impressed by the landscape and the problems exposed by the smart grid and all the challenges we're facing there. And then I hope that in the afternoon, we'll do the other way around. So that's for the power engineers, system engineers in the room, that you actually can also kind of catch up with the latest innovations and also what's happening now in the rapid, what we call this AI crazy drive. And then I'm going to just drop you a few kind of interesting hints regarding what we are going to expect in the afternoon today. Let me see. Okay, yep. I will probably just go one by one. So PowerWeb this year, we actually have the intention that we want to actually connecting both smart grid and AI. I guess the reason is actually also very straightforward. And I actually mentioned also in the previous keynote by Suzan is that nowadays AI companies are looking for power, and then smart grids and operators sometimes are taken by surprise, how to respond to that. And then nowadays you see both two actors, they are driving their own agenda. And then in the US, companies are trying to build micro nuclear power generators and the things, this is actually a sign of showing that the people are really run out of, power, run out of energy. So they try to get everything out of to sustain their growth in terms of what brings by the AI. And then what the pictures actually I'm bringing here is that this is actually a data center currently being constructed. And then the problem is that no matter how fast you want it, actually the supply chain is also still holding us back. So in that sense, this is a sign of problems that go beyond what people can, just put money on it. So it's not about just money, but it's actually even more than that. And then in terms of, for us, who are actually doing research, who are doing engineering and also making the system more sustainable, we should actually think about what we can do actually even more on top of that. And that's, for the whole afternoon, we want to bring you a different perspectives in the landscape from computer science engineering domain. What are the interesting elements, pieces, and components that can contribute? So that, we have this kind of a nice interactions between the power engineers, power systems, and also the computer science, computer engineers. And I remember a couple of keynotes and also in the morning and the speakers, you mentioned that when you are migrating your infrastructure to the IT, it is one of the problems that we are actually lacking expertise, lacking actually also understanding of each other. And I hope that, we are going to do actually a little bit better today. So very interesting thing I want to highlight. So that's actually one of the things I got in recently. Suzan mentioned that all the data sheets you recently reviewed sometimes are putting about the data before 2022 or even 23, and ChatGPT is released at the end of 2022. So the things actually we are missing here is actually really huge. And then this is just one interesting kind of phrase I want to throw. So nowadays, when you are playing with generative AI, generating 1 minute of video on your device, that's more almost like, playing PlayStation 5 for about 36 hours continuously. So that's actually, just give you a hint. This is the energy bill, energy consumptions we are trying to face in the upcoming years when everybody is embracing generative AI agents, and all the agents are start doing things by themselves, training, communicating, and doing all the business on behalf of a human. And this is actually the cost we should not easily just throw away. 1 minute to 33 or even 40 hours of continuous PlayStation playing. That's actually maybe a more interesting direct image that you can get. And of course, from our community in the Power Web and also from the computer science we are involved in Power Web, we also actually are looking into the problems. And then this is one of the paper recently being picked up by IEEE, is about, we should actually look beyond computing system design and also combining that in the context of climate crisis. And then as you can see here, this is on fire. And then that's actually the sign of, we are really facing a problems nowadays it is actually not easy, and actually people are start waking up. And that's actually why, I'm happy to see many people actually in the room today are very eager to actually see through the, boundaries of each other. And then, of course, this is the thing actually we have been already cooking in the past few years. And this is something we cooked from Netherlands, from the Lorentz. So if you're from Germany, that's similar like, Dachstuhl type of event. And then we actually gathered actually many experts from different domains to generate this vision. And we are actually going to probably run this next time. And then I hope that maybe next year or the upcoming years, we will see you also in the new discussions in our Lorentz in that. And this is the picture you can see here. So Suzan, Andy, and many of us, we are actually kind of, setting up the scheme to somehow expanding the reach of the research we are doing in computer science so that, we are not just lock up ourselves in a chamber and then everybody know there is a chamber effect. And that's actually not good for the overall societal challenges we are having. And then, maybe also back to one of the quick things Suzan mentioned is that we talk about future computing, future continuum. What exactly is that? So I will give you maybe half minutes quick overview. So this is actually a picture that we came up during the discussions with all the global experts on computer science and also engineers. So what you are looking at here is that we should avoid in the future that breaking the boundaries too much. What we should look at is that all the devices we have along the whole spectrum, they should be actually regarded like whatever we say, a pool of resources. And they should be continuously flowing back and forth regarding the requirements of the users, of the customers. So that we do not actually have to restrict ourselves on each single devices. And then this is actually where today in the afternoon we have people from cloud operators, from telecom. They will also kind of pitch the ideas, what we put it here, that along this computing continuum, the future computing, we have many challenges. And one of the ones in the center, in the middle there, is about the sustainability, that how we actually can build the future. And of course, many of us actually coming here from Power Web, from especially Power System, you heard about the word edge. And then in terms of, computer scientists, I want to show you that what we think about edge. So this is actually one of the pictures showing that, holistically speaking, many of us actually think that edge is the devices near us. It can be the device in your pocket, but then sometimes it can be the device actually from one hop away in terms of wireless communication. So we have a speaker from KPM today. For them, the edge is the base station. So that's like, the closest communication hub from your device to the edge. But then this is actually a floating concept, as I already mentioned, that in the future, we should not restrict ourselves into edge, device, clouds. It should be actually about the full computing scenario that you actually do not have to, draw the lines on the sand, say that, we do edge, you do clouds, and he does the device, and you do this and that. And then in terms of all the kind of communication and also the overhead of computing, I would say the picture here I show you here is just to give you a quick overview. In terms of edge, that's more like a sandwich in the middle. So this is actually up to debate, because I think this is the concepts that many of us, maybe from the system perspective, that we already know in advance. And then this is also just to let our colleagues from PowerWeb Institute, especially on the power system side, this is the edge from computer science engineers, what we are actually nowadays looking at. And of course, in terms of research, we will have many people today in the afternoon talking about different exciting research. But actually, these whole things on the edge, that many keynote speakers talk about the problems happening in the smart grids on the edge. It is actually by itself a big subject nowadays, growing very rapidly. So you have actually on edge, when you want to do computing and AI, there are actually many things. So each of the small box you see here, can be actually one or two or several research groups focusing on. So, and I think in TU Delft, if you ask me, what we have been doing in TU Delft, overall speaking, I would say we have a lot of people actually working on the upper tier. And this is for company, when you want to actually come to TU Delft, looking for collaborations, tackling problems, what kind of edge AI and problems. This is actually a very good way for you to locate the problem space and positioning. And from my side, of course, I want to mention that also, since I'm also driving this research agenda for many years, I also wrote a book on this one. And last year, I was also the program chair for ACM Edge Computing, and this year as general chair for the IEEE Edge Computing. So this is actually, at least I can tell you that community-wise, has been a lot of efforts going on. And then at this point, what the community actually was asking me the most is that what kind of domain we can contribute the most. And then, what I typically tell them is that, guys, you should actually talk to the people in the smart grids, talk to the people in the smart transports. And because those are the domains actually we face a lot of challenges, but then because of all the historical reasons, there was not so many actually fruitful and also maybe knowledge exchange. And that's, where the PowerWeb today, we would like to take one baby step, one by one. And then, of course, I mentioned about the logistic. So a couple of years ago, I do actually wrote this paper when PostNL 4 years ago approached me about, what they can do to improve the logistics processing speed and latency. We do actually had a kind of futuristic look over what's actually on the edge for them. So I hope that probably resonates to some of the power engineers today, mentioning that you realize now the problems, the opportunity are on the edge. And this is actually your counterparts in the logistic sector. So they also see the same trends and same opportunity and problems. And then also, of course, very quickly, in TU Delft, we have now a new green AI initiatives. And then this is a white paper we published recently. So we are rapidly collecting faculty members, partners, friends, university companies, government agents. So we would like to actually drive this together. So this is also in line with what Suzan just mentioned, that the problem we are facing now is actually kind of multi-facet. So we cannot just solve it as a computer science problem or a power engineer problem. And then so for all the things actually we have been pushing through, I just want to actually drop 1 or 2 lines just to show you that, the problems can be divided into different layers. But of course, when you come down to the real cases, this is one of the problems I actually faced myself several years ago, because when I was actually leaving the BMW lab from Munich coming here, I was actually looking at the transport domain issues, how we can save energy. And then as you can see here, it is not very straightforward. The cases, what Suzan mentioned is that when we look at the mobile networks, sometimes certain applications, they are not safety critical. But then if you come down to the safety critical domains, there is a lot of controversial and also difficult decision people have to make. So for this case, in terms of, when you are driving on a smart car in the future, do you actually value energy saving more or actually your personal safety even more when you are sitting in the car? So this is actually one of the potential problems that has been, striking me for the past several years. And of course, there is no free lunch. So even though every one of you get free lunch today, but the problem is that there is actually no easy free lunch. So you get the lunch today for free, but of course, that's the communication, the time you spent with us. So, and then I would say just drop the last few keywords. Just an example. So lots of things we talk about here, we have to balance. So on the right-hand side of the slide, you see the scale. So one of the things you can look ahead is that we need to find a different kind of balances in the future in terms of customer demands, application quality of services. So nowadays, as you can see here, simply speaking, we need to find the sweet spot. And that's actually a very important research question that we should ask every domain and every kind of a specific subjects. What actually is the balance that we can achieve? And for example, like here, everybody knows that, depending on the quality, people can tolerate. And also, you can actually make a trade-off between many of the KPIs. But then, how good is good enough? And that's actually something that's, from computer scientists, we can actually make a general universal kind of a statement. But then this, when you go down to the specific engineering domain, then that's where the things gets really ugly. And then that's, one of the examples. So, and I want to show you the beautiful side and also the ugly side of the whole thing. And then in that sense, if you want to understand a bit more, this is actually the talks in the afternoon we are going to bring to you. So we have experts coming from very different subjects, distributed systems, embedded systems, AI from the telecommunication partners. And we also have people going to talk about generative AI agents today. And even more, we have many people actually about the power engineers, but we also bring civil engineers to the room today so that you can also hear that, in the closely related domain, they are also facing similar challenge and then what they are doing there. So without, further dragging the time, I think we should actually go ahead. Yeah. Can you actually show me the time? Yeah. Yeah, exactly. So we are already kind of quite advanced. I would say we have actually half an hour in terms of coffee break. Yeah, because I think now this is probably the right moment, and then we get all the speakers probably prepared. So half an hour for the coffee break. Okay, very good. Yeah. So everybody probably you are tired. Please stand up and maybe talk to each other.